because you can't do it in reality. You haven't done it in reality. You can't measure it in reality. You can't prove it in reality.
This is we're making progress. This is at
This
least we're
picture
doing
actually
3D.
shows only one of those things.
Remember how Brian's logic said in that thing earlier that the FED guys only do it in 2D, right? Well, turns out Peter, he's doing it in 3D, right? This is 3D, right, Peter?
This is 3D, and I'm showing you how to measure this triangle in reality. That's why I have this azimuth angle circles here. This is the reality, actually.
Okay, well, I'm just looking at the triangle, right? The one at the top.
Yeah. But notice how from these 3 points on the sphere, we can derive 3 different sets of angles. This is the fun part. This is what I've learned here.
So we have the angle.
Yeah, just listen a little bit. We have the first set of angles are the angles on the sphere between the arcs. Then we have the line of sight triangle, the gray triangle, which is in a different plane. And that's a regular triangle with 180 degrees here in the middle. However, when we project those angles onto the horizontal plane for every theodolite station, we then get the azimuth angles, and they add up to exactly the same number as the spherical triangle on the surface. Welcome to the globe. This is how you would, in reality, measure the actual spherical excess by measuring those azimuth angles, and they would not add up to 180. They would be more.
What's the spherical excess then?
Here it is 15.14 degrees.
15.14.
Yeah, now if I change the triangle, obviously, I'm changing the triangle, it changes, right?
Yeah, how big can you make it?
I can make it as big as you want me to make it, Bev.
Can you make a 540 degree triangle?
Yes, I can.
Go on, show me what a 540 degree triangle looks like.
Close enough, 535.
Right. Does that look like a circle?
Not really.
No? That red line.
I could make it to be a perfect circle.
Is the red line, that's the circle. That's a 540 degree triangle, is it?
Spherical triangle, yeah.
Yeah. You know why they call that great? A great circle.
Yes.
Do you know why they call that a great circle?
I know. All these arcs
because it's actually a triangle with 180 degrees more than an actual circle, right? That's clever, isn't it?
No, that's not what they call it, the great circle. I mean,
well, that was a circle. You were just doing it then. It's a 540 degree triangle.
Dude, these arcs are always arcs of great circles. They're always great circles.
Yeah, but the 540 degree triangle is the great circle, isn't it?
All of these are great circles.
Yeah, but when you make a 540 degree triangle, it is the great circle. And it's great because it's got 180 degrees more than an actual circle. And that's because it's actually a triangle.
Bev, what are you talking about?
It's great.
Bev,
what would I know about geometry or anything like that, right?
Nothing, Bev.
But you did it for us. That was brilliant. You should do a Google presentation. Put it on your video channel.
How many degrees does a circle have?
How to make a 540 degree triangle that looks like a circle. Well, it is actually a great circle.
All of these arcs are great circles.
Did you explain this to your son then?
Yes, he's staring at it. All of these arcs are great circles.
Yeah. And when
This
you
red
make a
line.
540-degree triangle, it is a great circle.
No, it's not. It's on the surface. The great
Show
circle
your
has
son
to go
again.
through the center.
540-degree triangle. Look at it.
Are you saying that that the equator is a great circle? Yes, it is.
Yeah. And
But
that's the
every
500.
meridian
That's what
is
it
a
looks
great
like when you
circle
do a
too.
540-degree triangle, isn't it? But it's
Do
not
you see
really a
that these are
triangle.
also?
It's a circle.
Oh my God.
You can see it. You can see all of those curved lines all
Great
join up
circle.
to be the same curved line, which is actually a circle. And then you can call it a 540-degree triangle. That's great.
Okay.
So every great circle is actually a 540-degree triangle.
No.
Yeah. Yeah, and if you can put another point on it, you can make it, you just add another 180 degrees every time you add another point.
Exactly.
So you can make that same great circle, which is a 540-degree triangle. You could add another 180 in and make it a square with how many degrees? It'd still be like a great circle, right? But it works ad infinitum, right? Just keep increasing the angles within it by adding another point.
These are the angles between the planes.
Yeah, and when you make a 540-degree triangle, it's the
Yes.
same plane.
No. Look. Do you see these planes, these arcs? It may be hard to see.
Yeah, make the 540-degree triangle again.
Just shush it for 1 second. Each one of these arcs lives on a plane, okay? The angles are between those planes. Now let's stretch this triangle out. Just shush it, Bev. Whatever, it's almost 540. Well, it's impossible to see. But these planes face no, they overlap at this point. They overlap. There are three segments.
Looks like the same plane to me, that.
Because they overlap. C1 and B1 is one arc. B1 and A1 is another arc. And A1, B1 is another arc.
Yeah, geometrically, it's the same
yes,
circle,
if
isn't it?
you place them in such a position, then the angles between these planes add up to 540.
Mm-hmm. Yeah, each of those angles at that bit is 180 degrees, a straight line.
That's all there is to it, because you have kind of spread your triangle all over the sphere. That's what happens.
Yeah, straight line meets straight line meets straight line. 180, 180, 180, 540. It's just a circle. It's just a circle, but it's got 180 degrees more than a circle. That's great.
Oh my God, it's a different thing you're describing than a circle. You're describing three points in relation to one another.
Thank you, Bev. You saved me from this religion. I'm going because I'm become an atheist now. I can see it clearly. Good luck with this nonsense. Take care.
Yeah. Yeah, this ball geometry's it's like nonsense, really, Peter, isn't it? I mean, it's all right you doing this, but the problem is when you imagine it has some bearing on reality.
Why?
Well, because triangles don't have 540 degrees, and circles definitely don't have 540 degrees. Not even if you imagine the circle on a sphere being a triangle. Could you ever imagine, really, that you could draw a circle and make it 540 degrees and call it a triangle?